Okay. All right. So welcome to Legion School. So this meeting is going to be a long-running series of meetings to describe the internals of the Legion and Realm runtime systems. The plan is going to be that we're going to meet once a week, and we're going to alternate weeks. So we're going to start with Legion this week, and then we'll do a Realm week next week, and then back to Legion, and so forth. And the idea will be to describe the internals of these runtime systems. So I'm going to assume that like you're already familiar with the program model and probably a little bit of the APIs of some of these runtimes. Although like in the process of looking at the runtimes, we'll actually look at the interfaces and where they enter into the runtimes and stuff like that. So you'll learn a little bit of that along the way, but mostly this will be about how the runtimes themselves actually work and not so much how to use them per se. This meeting is going to be shared, with external people. So our goal is to like, allow anybody to learn about Legion Realm. So we are going to like record these meetings and post them on YouTube and stuff. That means that like, for folks at NVIDIA, if you ask a question relevant to internal stuff, I'm not going to answer it. But if you ask a question related to Realm and Legion, like I'll be more than happy to talk about anything that's open source and public, is all above board. Let's see. The meetings will be recorded, obviously, and I'll post them on YouTube so you can watch them later. So you don't need to come every week. In fact, you can skip weeks. If you're only interested in Legion, you can just come to Legion weeks. If you're just interested in Realm, you can just come to the Realm weeks. And that way, you don't need to come every week, and you can also watch recordings at like 2x speed on YouTube and stuff afterwards. I do want all these meetings to be interactive. So like at no point should you feel bad about interrupting and asking a question. Like the point of these meetings is to learn stuff, and like it's likely that your question is actually relevant to other people or maybe something that somebody else is thinking. So like stop me at any point to ask questions. That's the value of coming to the meeting in real time is you can stop and ask questions. Let me share my screen here. Let's see. Let's just share my whole screen. Okay. I do have a syllabus, and I will send this out in just a little bit here, probably after the meeting. Let me find, so let's see, I've got a Realm syllabus and a Legion syllabus. You can see the Realm syllabus here is much shorter than the Legion syllabus. But effectively, I'm expecting each one of those bolts to take one, maybe two sessions to handle. The Legion syllabus is a lot longer, so it'll take more time to get through all those things. So we'll just do this as long as it takes. But folks have things that are important. I can always reorder things, but this is sort of a natural order that I'm planning to go through, and I can send this out to everybody. I'll try to announce before each week, what we're going to talk about that week, so you can decide whether you want to show up or not. Okay, before I get started, does anybody have any questions, or can I jump right in? We'll start with Legion. Okay, no questions. All right. So let's see. And yeah, somebody can just keep admitting people in the lobby, whoever is trying to join. All right. So I'm going to do this whole school by looking at code. Like in a couple of cases, I'll probably share slides and stuff like that. But most of this will be looking at code. I'm going to do this on GitHub. Or sorry, GitLab, because that's where we keep the Legion Realm repositories, sort of the main branches. I'm going to do most of this I'll be doing this on the collected branch today, but hopefully this will merge down to control application and eventually down into the master branch. At some point, Legion is going to get refactored, and a lot of these types and stuff will move around. So the file names and stuff are probably not so important, but the type names I'm planning to keep all the same. So like, if you're wanting to refer back to this video later, all the types, you should be able to grep for them in the code and find them and stuff in the places you expect. So the place where I want to start today, I actually went back and looked. We did this Legion school about 8 years ago, and I looked at how we did some of the then, and I think we can do it better the second time. So what I'm going to start with today, I want to start with a brief introduction to what happens when you launch a task in Legion, because I think it's instructive to sort of get a feel for probably one of the more important abstractions that exist in Legion runtime, which is our pipeline. Legion operates like a out of order processor. It has a 7-stage pipeline. I want to look at how like a task, comes into the runtime and starts executing through those pipeline stages today, so you can get a feel for what that looks like. For anyone that's ever implemented an out order, multi-stage pipeline processor and like Verilog or something, this will all look incredibly familiar to you. If you haven't, that's okay. We'll try to ease you into it gently. Okay, so let's start with the Legion API. How do we launch a task? Right, so if I go to the Legion header file, right, the way you launch a task is you make one of these in your application code. You make one of these task launcher structs. You configure it with your task ID, any predication, the name of the mapper you want to use. You add a bunch of region requirements and futures and other stuff, and so you populate this whole structure with like the configuration of the task that you want to launch, right? And then you call this method execute tasks, right, on the runtime itself, right? And that you pass in your context, your task launcher, its output requirements. We'll ignore those for now, and it gives you back a future saying, that this task is when this task will actually be done and stuff like that, right? Now, this feature, like unlike a lot of other task-based systems, features in Legion are almost irrelevant most of the time. The most important thing are the region requirements that you launch on the task, because that's what's actually going to determine your dependence analysis, right? So like, you can use features for dependencies and stuff like that and passing values, but the common paradigm in Legion is using regions and stuff for doing data. Okay, so let's actually look at what happens when you call this execute task. So the first thing that we go into, you'll notice there's this legion.cc file. And if we search for execute task, right, you'll see that there's a little bounce here where we bounce this off of an internal runtime structure. And you'll notice this pattern in this legion.cc file a lot, where everything in here is pretty much just a bounce, like sort of a trampoline onto some internal runtime or internal context and stuff like that. And the reason for that is that I actually, this is a little digression, but I want to enable this API at some point in the future to be introspected and sort of traced or sort of captured, so you can translate Legion calls if you want to. Kind of like, for those of you familiar with MPI, MPI has the PMPI interface, right, where you can sort of hook all the MPI API calls and rewrite them or profile them or whatever. And the idea is that you could do the same thing with Legion in the future. So this legion.cc file pretty much has a bunch of bounces and trampolines just to make sure that we could hook the Legion API at some point in the future, pretty trivially, for profiling or rewriting, or alternatively, like one thing that I've thought about is like maybe you could do an RPC call in here, right? So if your client program was running somewhere separate from like the Legion runtime, you could effectively take all these things and serialize up the launchers and then ship them over a socket and deserialize them and then pass them into an actual runtime running somewhere else. But for anyone that's wondering like why you come into legion.cc and all it does is trampoline off onto some other part of the runtime, that's your answer for you. So this one bounces off the runtime. You'll notice a lot of calls actually will distribute through the context instead of the runtime, and I'm probably going to rewrite this one as well to do that also. But for now, this will bounce off our internal runtime data structure, and we'll talk at a later session who makes these how you set up the runtime and all that stuff, but that's not particularly relevant to us. And really all this does is check that the context is a real context. It's not a dummy context, and the user hasn't passed in some invalid context, and then it dispatches to this context object. This context object is to the user an opaque handle, right, that effectively tells you, it's a way of naming all the state of your parent task that's launching the subtask. And we'll look in a lot greater detail what these contexts are in the future, but you can think of them as like a context is associated with every parent task that's launching subtasks and sub-operations. And so the place where you actually find this context is in Legion context.h, and there's a couple different contexts. So there's the base class context, which is sort of the base for all kinds of contexts, this task context. And then there's a couple of derived versions of it. So there's the inner context, which is sort of a task which can launch subtasks and sub-operations and so forth. We also have leaf context for tasks which cannot launch subtasks and things like that. And for more fancy stuff that we'll get into later, there's like replicated context for handling control replicated tasks and so forth. And we'll talk a lot more about that later. But for now, we're just going to follow this into the context and see what it does when we try to launch this task. So first, if we search for leaf context execute task, you'll notice that effectively, if you've told the runtime you want to inline that, we allow inlining of tasks into leaf tasks, which is totally cool. But if you're not inlining, you'll get an error saying, hey, you can't launch a subtask in a parent task that you said was a leaf task, right? And so you can see, if you dispatch to a leaf context, you'll end up, most likely in this error message. But, the common case and the more common cases is, actually if you're in an inner context and you execute a task, all right, we're gonna do something pretty simple. So, the first thing we're gonna do, we have some tracking for tracking like profiling and stuff of this API call, so we know how long we spend in the runtime. We have some provenance tracking, so we can know, effectively where did this launcher or who called into this task, and we'll track the provenance information for you. We've got a little check here to see, like, was your task predicated false? Like, was the launcher just a simple case where they set the predicate to false? If so, like, there's nothing to do. We can just, return the future result from that. But, the common case here is we ask the runtime, hey, give us a new individual task object, which is going to represent the execution of our task as it goes through the pipeline. We'll take a look at this type here in just a minute. We're going to populate this task with all the data from the launcher. Some special arguments here, but effectively what this is doing is just filling in this task data structure with making copies of all the data that we need from the launcher. Effectively, whenever you call into Legion, we copy all the data out of the launcher so that, as soon as you return, the user can start reconfiguring that launcher and using it for something else, right? And once you do that, you get back a future that you're going to be able to return from this thing or from this function. But before you do that, you actually call this execute task launch method here, which is actually going to kick this off to the runtime. So let's actually take a look at that method. Execute task launch. And you'll notice this one actually works over all kinds of task launches, not just single tasks, but also index tasks. And we'll look at, again, I'll show you the type hierarchy here of the tasks. It's going to become important in just a moment. But what we do, let's assume we're not inlining, we're not doing any inlining here of this task. We can ignore that for now. So the first thing we do is we have a little check here to help the user to see, like, if they have any map regions before they launch that this task is going to need. We'll actually help them unmap it and then remap it, after we launch the task. There's some special logic here to help warn you about, Legion's doing some extra work for you that you probably should have done yourself, but those are all just sort of performance warnings. The most important thing that happens here, though, is that we call this method add to dependence queue. And what this does is this puts this operation, this task, into the pipeline. So everywhere that you see this call add to dependence queue, that's effectively kicking the task off asynchronously into Legion runtime and saying, please go run this through the pipeline and execute it. And at this point, after I do this call, I'm completely done with, my responsibilities as this calling function. And I get to return asynchronously back to the client program so the client program can keep running ahead and doing whatever it wants to do, like launching more tasks, right? And, one thing that's important to realize here is that, like, and this is the very beginning of how you'll see continuation passing style in Legion, is that, effectively this task star object, as soon as you call this method, you cannot touch this task star again after this API call, because once you put it in the runtime, conceivably it could actually run all the way, this thread could actually end up, you could imagine a very, unusual scenario where the thread that actually did this API call, as soon as it returns here, maybe it goes into this remap call and then it blocks, or it gets preempted by like the OS thread scheduler or something, right? This task could actually run all the way through the pipeline and finish executing and complete and commit and all those other things and return. And then if you tried to refer to it, past this API call, right, it would actually be an illegal access of that task object, right? So one thing to keep in mind is just like, you want to make sure that, when you're doing continuation passing style in Legion, once you kick things off asynchronously into the runtime, right, you have to be very careful that you've, done all your modifications and changes and stuff like that, okay? So once you kick this, once you kick this task into the runtime, though, you can pretty much return. The only other thing we do here is remap any regions that we unmapped here to help out the user to avoid deadlocks and stuff like that. But at that point you're done and you're returning back to the client program, and then this task is executing asynchronously, but while still maintaining its sequential semantics. Okay, any questions so far about all of that? Okay. All right. Let me actually show you a little bit of the type hierarchy. I want you to see, what this individual tasks was that we. So let me step back here. There we go. So you remember that we got this individual task object here. I want to show you what this is and where to find these things and where this type comes from, because it's actually quite important. So this type here, this individual task. Oh, did I type it wrong? I think I did. Type the URL wrong. There we go. So this individual task is effectively a class that represents all the state that we're going to need to actually execute a single task, right? And what I mean by an individual task is like effectively we've launched just one task that's going to run on some processor somewhere and actually do some computation. And this is in contrast to doing, say, like an index-based task launch in Legion, where you create a bunch of tasks concurrently with a single API call, right? So we'll look at like index task launches at a future date, but I want you to see the type hierarchy here just a little bit, so you can see how this works. So this individual task you can see is an instance of a single task. So if we look at the single task class, right, this is sort of a base task, or below. It's not the base task, but it's a base class of an individual task, and effectively serves for all the tasks that are going to actually be like a single point task or a single individual task that are going to run on one processor, right? So you can also see there are things that derive from single class or from single tasks, right? We've got the individual tasks, and we've also got point tasks, right? And point tasks are the individual tasks inside of an index-based launch. And again, I'm going to look at those later, but just realize that there's like other kinds of single tasks beyond just individual tasks. There's also shard tasks, but again, another special case. So there's effectively 3 kinds of single tasks that you can be aware of, and we'll just stay focused on this one today. But just to be aware of that. And then you also probably noticed that single tasks, right, it inherits from task op, right? So if we look at task op, right, this is a base class of all tasks, including multitasks, which are there's also multitasks which inherit from this task op here, right? And there are several kinds of multitasks, like index tasks inherits from multitask, and slice tasks inherit from. I can type. Slice tasks inherits from multitask. Anyway, there's a whole type hierarchy here I just want you to be aware of. Again, we'll talk at more of those types in detail, but let's come back to this task op class here. And you'll notice that this task op here, this is the base type for all task operations, and it inherits from external task, which, just for a little digression here, that's a publicly facing interface that we allow, that is available to mappers and stuff. So that external task is effectively a rename for this task right here that you see in the legion.h API, right, which is effectively like the user interface for all the things that occur with the task. So that's what that external task thing is. But more importantly here, you see that task op inherits from predicated op, right? Tasks are an operation which can be predicated, right? They can have a predicate that the user passes in whether they're going to run or not. So the place to find out about where predicated op comes from is actually in legionops.h. So we'll hop over here to the operations header file and look at predicated op. There we go. So predicated op is the base class for operations that support predication. You'll notice that this also inherits from memoizable op, which are all the kinds of operations which can be traced in Legion. Again, we're going to talk about tracing at some future date, but eventually we make it here. All memoizable ops are also inheriting from this base operation class. So, and this is the base. This is really the base of all operations and stuff inside of Legion, right? So everything that goes through the Legion pipeline has to be an instance of this operation class. And you can see that there's like all sorts of operation kinds, right? We've got like dozens of operation kinds that can run through this pipeline inside of Legion. again, today we're just going to focus on tasks, but I do want to show you what the pipeline looks like. And the pipeline is effectively implemented in terms of, overriding virtual methods on this base operation class. So pretty much every operation that goes through the pipeline is going to get a series of callbacks for each of the stages in the pipeline. And what's going to happen is in your particular implementation of an operation, you're going to override those virtual methods to do different things for that particular class. So let's actually find those callbacks here. Okay, so inside of this base operation class, there are a series of callbacks that you get, and they all start with trigger underscore. So then I think there's 7 of them, I believe. 2, 3, 4, 5, 6, 7. There's actually 8, and one of them is a duplicate or sort of an intermediate stage. But anyway, you can think of these as the stages of the Legion pipeline, right? And what's going to happen is once you kick an operation into the Legion pipeline, what will happen in order to implement like any one of these operation classes, like as the operation goes through the pipeline, you'll get a callback as it proceeds through that particular stage. So, the first thing that will happen is assuming you have a pre-pipeline stage, you can always opt out of that one. But like you can think of pre-pipeline stages like your fetch and decode kind of stage in your normal processor, right? Where you're going to sort of do any sort of preliminary work that occurs before starting the operation, right? And then the next stage is the logical dependence analysis that you'll hear me talk about a bunch. And so this is where you're going to perform your first pass on dependence analysis. And we'll talk about the distinctions between logical and physical dependence analysis at a later date. But this is the logical dependence analysis where you're going to sort of figure out where your first dependencies are on any prior operations before you actually map. This is the intermediate stage where like some operations need to be controlled by the mappers, so they won't actually map until like the mappers say they're ready to map. So things like tasks actually do have this because like they need to go through the mapper, and the mapper needs to pick them for mapping, right? In the select task to map API, mapper API call that many of you are familiar with on the user facing side, right? This is where we'll actually stick these things on the ready queue to tell them like all their dependencies are satisfied and this operation is ready to be mapped, right? The next stage of the pipeline is your physical analysis, actually doing the mapping onto a particular target processor and picking instances for all of your logical regions, issuing any copies, hooking up the realm event graph for actually doing the computation for this operation and so forth. Next is your execution stage of your pipeline, where you're actually going to actually run the operation. Some operations don't have to do anything here. In fact, a lot of them don't. Like most things that are not tasks actually can skip this stage because like they've already done all their stuff by kicking things off to realm. But for things like tasks and so forth, right, the trigger execution is what will actually launch the task into realm and enable that to actually start running somewhere. Trigger resolution is handling of speculation and stuff like that. So you can actually deal with like misspeculation and faults and things, or actually just misspeculation here. Trigger complete is the last stage of the pipeline for assuming that you're not doing anything with resilience. So once you get the trigger complete call, effectively you're finishing up all the effects of the operation, and you're telling any downstream tasks that this operation is actually done, right? And trigger commit actually says that to the runtime, we know that this call will never roll back because of a resilience issue, right? So if someone actually reported a fault downstream, we might need to roll back and restart, this particular operation. And once you call trigger commit, that effectively is guaranteeing that that's never going to happen, right? And so you can actually clean up the operation and get rid of any resources that it's holding and so forth, right? And so this is the 7-stage pipeline. And if we actually go look, let me actually pop up. Actually, we'll hop over here and we'll reuse this. We'll use this window here. Let's go back and look at the individual task interface here. For some reason, it's not typing, and I'm typing my URLs wrong today. Okay, where's Legion tasks? There it is. Go back to the individual task here. We scroll down here. And you'll see that we've overridden a couple of these methods here, right? So you can actually see three of the stages of the pipeline that we saw over here, right? These are actually being overridden. Now, one point of a little bit of, I won't call it embarrassment because there's good reason for it. You notice I'm not actually using the override keyword in C++ here to declare the override. That's because Legion was originally written and had to support C++ 98 for some very old supercomputers. And so like I haven't gone through and updated, all the virtual overrides and annotated them yet, but that will make it clear what's actually happening here. But you can actually see, all of these callbacks here happening on this individual task. Now, in some cases, some of the other overrides are actually happening on base classes. So things like trigger complete and stuff are actually being overridden in some of the base classes for individual tasks. So if I search for trigger complete here, am I in the right base? That's a slice task one. Let's see, where are we here? Right, so like trigger complete is actually, trigger complete and trigger commit are actually, one too many there, actually overridden in the task op base class, right? So just be a little careful there that like some of the overrides might have occurred in base classes and not necessarily in like the most derived type. But certainly you can find cases where like where most of the stages of these pipelines are being overridden. Okay, so let's actually go look at some of the code for some of these stages, just so you can get a brief feel for what's actually happening inside of some of these things. So we look at individual task. We'll do trigger pre-pipeline because it's really simple. So this is the individual task trigger pre-pipeline callback that you get from the runtime as it's going through the first stage of the pipeline, right? You'll notice that like, if you haven't already selected your options for mapping this task, right? This is where you actually get your callback to your mapper to select the task options, right? If you try to inline, you get a nice little warning and stuff like that. We also pre-compute a couple of things sort of ahead of time, before the task actually starts, doing its more sophisticated dependence analysis. We can sort of pre-compute some stuff ahead of time. Stuff like, getting some of which parent region requirements, your region requirements are deriving their privileges from, finding those privilege paths and stuff like that, or checking for like aliasing of region requirements, which is illegal, right? We do some of those checks in here because they can kind of happen beforehand. And then as soon as you're done, you can actually just return and you're actually done. Similarly, here's trigger dependence analysis, right? We actually call a base class method to perform the base version of this. And then what we do is, quite simply, just at a very high level, sketching what happens, we iterate over all your regions that you asked for privileges on as part of the task. And we go into our region trees and we perform dependence analysis to find out, what prior tasks and operations were using the same regions and start hooking up mapping dependencies and stuff like that, right? And so you can effectively, figure out, you can sort of do this, we'll talk about this analysis in more detail later, but very high level, it's a very simple thing, right? And if you look at perform dependence analysis or perform base dependence analysis here, I think we're just hooking up dependencies on, it's actually right here. We're actually just performing dependence analysis, like hooking up future dependencies and stuff like that, and doing some other basic work. But really, it's quite simple. And then here you can see, here's the trigger ready, stage of the pipeline, right? We can ignore some of the special cases here. The most important thing that happens is, we actually get put on this ready queue, and we'll look at this ready queue at a future date. But really, what this ready queue is doing is just like, this is the ready queue that's visible to the mapper in select task to map, right? And so this is the queue that tells the mapper, hey, here are all the tasks that are ready to map. Tell me which ones you want to map now, or you can delay that mapping until later if you want to implement like a stealing algorithm or something in your mapper API. Importantly, this is the first one point of distinction that is worth pointing out. You notice the trigger pre-pipeline and trigger dependence analysis, as soon as they return, that's effectively the end of their stage, and that's true of those two stages. But all of the other stages here, like in trigger ready, trigger mapping, trigger execution, trigger resolution, trigger complete, trigger commit, there's actually so I'll highlight these. highlight these here, but these 5 stages after these first 2 effectively require you to do additional work to complete the stage yourself. So these 2 stages up here, trigger pre-pipeline and trigger dependence analysis, right? They'll be considered done as soon as you return from this callback from the runtime. But all the rest of these here have a corresponding API call that you have to invoke, to continue making things happen. So for example, in trigger ready here, what we had to do was we had to call enqueue ready task, right? And that effectively put the task on the ready queue of stuff that like the mapper was able to see and actually continue doing things with. Similarly for like trigger mapping, there's a corresponding call down here, and I should really move some of these things closer together, to complete mapping, where you can tell the runtime that we are done with the mapping. So just because you get the callback from the runtime doesn't mean that you're actually done, right? You're not actually done until you call back to the runtime, in true continuation passing style, right, and tell it that you're actually finished, right? And you can see there's corresponding API calls for each of those 5 stages here, right? Effectively saying like, that you can call back to the runtime and tell it when you're actually done with that particular stage of the pipeline. So one thing that's interesting here is like in some of these API calls, like say in trigger mapping or something like that, you could actually do something like, you get this callback, you don't have to complete the stage right away, right? You could go off and kick off some continuations, some like other meta tasks to go off and do some stuff, and then you can return, right? You don't need to actually, just because like you've returned from trigger mapping doesn't mean that the mapping stage is immediately over. It's not over until you do the call back into do this complete mapping API call, right? And only once you've done that will that stage of that operation actually be finished, right? And so you can kick off your continuations. Those continuations can go off and do other stuff, right? And then once your continuations are done, then they can further invoke the continuation of calling complete mapping. And once you've done that, then you'll actually finish the mapping stage, right? And so there's 5 API calls here for doing other things. There's some other things for resilience and stuff. You can probably mostly ignore some of these things down here, but these 5 right here are actually really, I should really include enqueue already operation here as well. These 6 are actually incredibly important, as part of the continuation passing style of Legion. And so if you come back over here to like trigger ready, you can see we're actually calling enqueue ready task here, and that will put it on the ready queue, and that's the continuation, right? And effectively you can, so you get your call here, and then you can call enqueue ready task, but you don't have to call enqueue ready task before you exit this function. You could actually like launch a continuation and then eventually call enqueue ready task later, right? And we'll see that style, that continuation passing style, a lot throughout the Legion runtime. And so and I actually say like this is one of those things that makes Legion, both incredibly high performance at what it does. Like it's actually solving a really hard problem, and continuation passing style is a really elegant way to go about solving that problem. But it really puts a much higher cognitive load on you, the programmer, because like you've got to keep all your continuations straight and stuff. Unfortunately, like we can't implement Legion in a functional programming language and have the compiler automatically do all the continuation passing stuff for us.
Question.
Yep. Yeah.
Can you explain a little bit how you implement the continuation passing style? Do you have a separate compiler for this, or do you?
Nope, it's all done by hand.
Okay.
Yep, and that's what I mean. Like, we'll see some examples of continuations later where like we actually kick off meta tasks using Realm to actually be our continuations. So I mean, I guess the short answer to your question is we'll use Realm tasks to make continuations, right? And they happen asynchronously and go off and run at their own schedule, right? And that's what breaks the return, the return semantics of things, is like kicking off asynchronous tasks onto Realm to do things. So yeah, but we'll talk about Realm tasks probably not next week, but maybe on the second Realm session, I think is on the syllabus, like what a Realm task is. But effectively, think of it like that. The Realm runtime underneath of us is what's going to manage the asynchronous execution of continuations and stuff like that.
Got it. All right. Yeah.
Yeah. And so for now, I'm waving my hands a little bit and saying like, there will be some asynchronous, function call mechanism, right? And I'm not showing you what it is right now, but I promise you that it's there, and that's where the continuations are going to come from. Okay. All right. Let's see. So yes, I covered, effectively, you have to do these callbacks back into these into the runtime to effectively say when you're done with each of these stages, and that's the point where you actually do those. And in fact, if you actually look at like the base, let me actually show you. If you actually look at some of these API calls in the base operation class, you actually see there's like no-op versions of these things. So let's see. Right, so like these are like effectively, if you don't override these methods, right, the operation will actually go through like sort of the no-op path, right? So if you call trigger ready, you get an enqueue ready operation call, right? If you do trigger mapping, we actually complete the mapping and then we trigger the execution and then we complete the execution right away, right? If you get trigger resolution, we're actually saying you should never hit that. These assert falses will go away at some point in the future once I merge control application and turn these all into aborts. But anyway, trigger complete, and you see turn around and call complete operation right away. Trigger commit, turn around and call commit operation right away. So like, conceptually, you could actually like, if you want to do like a little exercise, you could actually make like a no-op class that inherits from operation. And then you could try like adding an API call to Legion API that will do a no-op and like, run it through the pipeline, and you could watch it do all its run through the pipeline and execute and stuff like that. But it's totally possible to implement like a no-op and just by inheriting off of like the base operation class and so forth. Right, and I guess I remember now, the reason that this should never be called is that like only predicated tasks should ever get this this callback from trigger resolution. So anyway, if you're ever wondering like, if you ever want to see what the default implementation of any of these methods should be of these stages, you can always find them here in the Legion Ops class. One thing I should talk a little bit about before I move on here is ordering of these stages. So, one of the interesting things about this pipeline, coming back to these 8 API calls here, one interesting thing that can happen here is that, effectively the runtime only guarantees ordering of operations like running through these pipeline stages in a particular order for one stage, and that is the trigger dependence analysis stage, right? Because like the way to think of this is that, let's say I have 2 task launches, like calling execute tasks like we saw earlier, and we kick off, the first task asynchronously, and then we kick off the second task asynchronously. Those 2 tasks do not have to run their trigger pre-pipeline stages in order. The runtime can actually reorder their trigger pre-pipeline stages. So effectively, they could run in parallel, they could run in either order. There's no specified ordering. The only place where you get guaranteed ordering of all the operations going through a particular stage of the pipeline in program order that they were launched for a particular parent task, right, is this trigger dependence analysis stage, right? So effectively, you will see the callbacks to trigger dependence analysis for each operation, whether it's an operation or a task, right, in the order that they were launched by the parent task, right? And we guarantee that. And that's necessary to get the dependence analysis right. And so you can assume that, you can safely assume that all of your callbacks to trigger dependence analysis will occur in the program order of the launch tasks and operations. After that, you've lost all ordering unless you've explicitly managed it yourself, right? So one thing that you can do, like if you want to imply ordering of the callbacks to trigger ready and trigger mapping and stuff like that, the way to do that is adding mapping dependencies during this logical stage of the pipeline, right? So you can effectively create dependencies, we call mapping dependencies, between operations during this stage of the pipeline that will then ensure that there is an ordering, that effectively like, if let's say task A that we launched, came through first and recorded itself, and then task B comes along, and in this trigger dependence analysis stage, it decides that it wants a mapping dependence on the task A, right? Effectively, maybe task A wrote some data and task B is reading some data on the same region, right? So we record a mapping dependence. What that will guarantee is that you won't ever get the call to trigger ready for task B until task A has actually seen its trigger mapping call and actually called complete mapping, right? And the mapping process for task A is actually finished, right? And that will, and once that has occurred, then you will see the trigger ready call for task B occur. So when you record mapping dependencies during this stage of the pipeline, which you're guaranteed to have happen in program order, right, then that will, any dependencies that you add here will help, you figure out your ordering for like the mapping stage of the pipeline and so forth, right? But like for these downstream stages, you can't assume anything happening in program order, after this stage, after trigger dependence analysis, you've lost, the sequential semantic, the original sequential semantic. So you have to add dependencies and stuff yourself, in the form of mapping dependencies or anything else to enforce the ordering of things. The runtime is free to, optimize away and do all sorts of things out of order and stuff in these stages of the pipeline after you've made it past this stage. So that's something that will become very important, and we'll talk about, how we actually, use that invariant, like that this stage happens in program order, and then how we maintain the necessary downstream dependencies, through mapping dependencies and stuff at a later date. But I do want everyone to be aware of that, like, effectively, you might be surprised to see, operations getting these callbacks, out of order with respect to the original program, when they get into these stages. One other point of ordering, these mapping stages and execution stages can actually get you can actually get a call to trigger mapping and trigger resolution in either order, right? So you might actually see the call to trigger resolution for a particular operation before the call to trigger mapping, because maybe like the resolution for any speculation stuff finishes first. So like you can get either mapping or resolution in either order, but you'll always be guaranteed to get all three of these stages before you get trigger complete. And you'll always be guaranteed to get trigger complete before trigger commit for any particular operation. So like, effectively the way to think of it is you always get this one first and this one second. You might get these four in any order, and then you'll only get this one after all of the prior stages up here are done. And then you'll only get trigger commit after your completion stage is done. So at some point I really should draw a diagram for that particular set of dependencies. But for any operation going through the pipeline, you might see some of these calls. You might like see trigger resolution occur before you get your call to trigger mapping or whatever. And so just like don't necessarily assume that some of these stages will actually occur in this particular order that these function calls are listed in. One other thing that I will mention here about like the callbacks or the continuation calls to actually complete some of these stages, you'll notice that pretty much all of these API calls take a runtime event that you can pass in. And that means that like just because you've done this function call into Legion saying like, hey, we've actually finished this stage, doesn't necessarily mean that like the stage is actually done. You can actually give an event saying the stage will actually be done when this event is triggered. And if you're wondering what RT event stands for, it stands for runtime event. And that is in contrast to AP event, which are application events. Legion actually enforces a type, a dichotomy between realm events to manage like, effectively runtime events. RT events are events that are internal to the runtime and are specific to like runtime only stuff, whereas AP events are stuff relevant to the application computation. So we actually segment the realm event space, and we'll talk about realm events next week and everything. But we're actually going to segment the event space so that we can isolate faults and stuff that occur inside the Legion runtime versus faults from like applications getting the wrong answer or having bit flips or stuff like that. Anyway, that's what an RT event is. But you can pass in an event to pretty much any one of these API calls to say like this will be the event that will trigger when the stage is actually complete. So it's like it's super asynchronous in that regard. Okay, so if I jump back, I've got like 15 minutes left, so I do want to finish getting through this individual task. But so this individual task, it gets a trigger ready call and queues itself as a ready task. At some point, it will actually get a call back to trigger mapping. Let's find the right one. Here it is. So like you'll see this one actually occurs on a single task, right, which is the base task for individual task, right? There's a couple of different cases here. I'm going to ignore the remote case where the task is actually executing or mapping remotely. The more interesting case is like this case in here. Again, let's assume we're not inside evil must epoch launches. We'll talk about those at a future date. But effectively, what will happen is the task will do its performance mapping, right? Once it's done with that, it will either distribute itself to a remote node or launch itself right away, right? And effectively, that will actually kick the task off to realm and actually have it run. At some point, it will actually execute, and you'll actually get a call back to trigger complete. That's the slice task one. Let's see if we can find the base task one. So you'll see this one is this callback to trigger complete actually occurs on the base task op, right? Legion actually has, for a task to be considered complete, we actually have two criteria for that to occur, right? One is we have to have actually finished running the task and have it actually be done, with its execution. There's actually a second stage, which is we actually have to have any subtasks that task actually launched off also be complete, right? So completeness is a cumulative, property, right? So a task is only complete once it's done running and all of its children are done running, right? And so we actually have to see if have we received the callback saying that all of our children are complete? If we have, then we can actually call this trigger task complete method. And what that will do is it'll do some cleanup work. It'll actually clean up the region tree context, and we'll talk about what all those are later. If you're running remotely, it'll send some state back to the origin node where the task was launched from. But eventually, you'll see that we get down here and we actually call this this complete operation method, right? You can see we actually have two calls to it. One if we have some outstanding effects to pass back, into the runtime, and one in case where we don't, where we just call back to complete the that stage of the pipeline, right? And once you do that, you'll get the call to trigger commit. Let's see if I can type. And again, there's another cumulative property here where you can only consider a task committed once all of its children are committed. Get the same callback to trigger task commit. And again, there's this callback to commit operation, which will actually clean up this task and tell it that it's done. And actually, there's one additional stage where after this operation is committed, the runtime will actually deactivate this task. Let me actually find. Let's see if we can find individual tasks deactivate. And what this does is we actually don't free up this individual task. We actually don't free the object itself. We actually have pools of these objects. We actually reuse them, and we'll talk about why that is at a future date. But effectively, we clear out all of our data structures and stuff like that. You can see there's a call to the base task or base class here to deactivate farther down all the types down the inheritance hierarchy. And then we're done with that. We actually pass this object back to the runtime so that at some later date, inside the context, it can ask to get another. If we go back to, I guess we lost the. We'll pass this object back to the runtime, put it back in the pool, and then it can get pulled back out of the pool again, by the runtime at a future time when somebody else wants to launch a task, and we can reuse this this allocation of this individual task, and that cleans everything up. So that's very high level, sort of outline of the Legion pipeline and seeing an individual task go through it. I've skipped around about a lot of each of these stages and what they do. The whole process of digging into the runtime will involve investigating what's happening in all of these different stages throughout the rest of the runtime. But the foremost thing you always want to have in your head, whenever you're working on the Legion runtime, is thinking, if I'm looking at a piece of code, let me think about which stage in the pipeline I'm in, right? And make sure that I'm doing things consistent with that stage and not with, some other stage, right? So you always want to have in your head, I'm working on an operation running through this pipeline inside of Legion. Which stage am I in? What am I trying to accomplish? And what invariants do I have and do I not have when I'm working in that particular stage of the pipeline? At some point, as we go through some more of these operations, we'll look at the individual stages. We'll look at how different operations implement each of these individual stages, because a lot of them are quite similar. There's some nuances to some of them, but in general, that's the way to think about, sort of this callback and then continuation method of working through the stages of the pipeline. So that's everything that I want to talk about today. What questions do people have? We've still got 9 minutes left before the end of the session.
Yeah, so Andre here. So since this is C++ 98 code, I assume
it was. It's actually 11 now, but I haven't fully complied with 11 yet. I haven't used all the features of 11, but the new minimum version of Legion is 11. Yep.
So for example, I see future here. So are you using standard future?
No, that's the Legion future class. Legion futures are quite different than standard future because they have to work on distributed systems, right? So yeah, if you actually look at the Legion,
they're not interchangeable with the new.
No, they're really not. Let's see. Yeah, I mean, if you go to the we go to legion.h here, you'll see in the public facing API, there is a feature class here that you can go poke at, but Legion features have to work in distributed systems, right? And so you have to be able to refer to them everywhere. And yeah, it's quite different than standard feature. So yeah.
So no multi-threading, new C++ 11 and above multi-threading abstractions like package task, locks, atomics.
So
all of that you had to kind of custom.
Well, Realm is actually going to provide all that functionality for us. And so like, you know, we're not going to sit on top of any threads here, right? So all this is built on top of tasks in Realm, right? So like, there's no, actually, you'll actually notice that like,
it's too low level for, as far as Legion is concerned, this is too low level. It doesn't care.
That's right, yeah. In fact, like, yeah, like the concept of a thread won't show up anywhere in the Legion or the Realm APIs, right? Realm uses threads internally, and we'll actually see some examples of that when we look in the Realm runtime. But like everything in Legion is written in terms of tasks. So not only is Legion a tasking runtime itself, but the runtime itself is built on top of Realm tasks, right, and continuations and stuff like that, right? So you want, that still requires like locking and synchronization, and we'll talk about how we use locks and stuff later, because you can have tasks that are trying to access the same data structure concurrently. Right, and so you do still have to worry about concurrency and parallelism and stuff, but the concept of a thread won't appear anywhere in here at all. So,
and a similar question for, I noticed that there's quite some usage of raw pointers. So again, why raw pointers? Well, one reason is obviously because there were no smart pointers, at least not in the standard template library. But any plans to maybe switch? Because typically smart pointers are a big help with eliminating some bugs.
They can be. I actually find that smart pointers are actually really good at things that are not continuation passing style, where like the lifetime of an operation is tied to the stack, right? Lots of things in here are not going to be tied to the stack because like we're going to make an object and pass it to a continuation, and that continuation might pass it to another continuation, and then like in the third continuation it would get deleted, right? And like a raw pointer is like, it's kind of required in that case. Yeah,
it's gonna expire because of the scope problem.
That's right, exactly. The scope is going to go away, and the smart pointer will be not quite what we want. So
all right, thank you.
I had a question about the 7 stages pipeline. So you mentioned that the trigger dependence analysis is the only one that's ever going to be run in parallel, and if you want to,
are guaranteed to be in order, in program order, like this, you launch the tasks.
And it's the one that if there's some dependence, you better note it there, otherwise all bets are off. Right.
That's right. Yes.
I'm thinking of the case where 2 tasks, let's say task A, task B, task A is reading like the first half of a region, and task B is reading the second half of a region. So they are technically independent, right? So the tasks themselves could run in any order, but later the mapper decides I'm going to use the same instance for both. So in that case, do they, is there, like, where would that dependence, now there's a dependence, right? Because they're essentially, they're using both halves of the same memory, of the same buffer. Is that
that's actually okay. That's actually okay. Like Legion will actually tolerate you mapping those in either order. So you don't actually need to record a dependence. Like we'll actually see the physical analysis, but the physical analysis that we'll do in this trigger mapping stage will actually be precise such that, even though they're both using the same instance, they can actually map in parallel. And we'll talk about how that works. Now, if they overlapped in any way, even if they were partially overlapping, then you have to record a mapping dependence between them to guarantee that they map in order, right, with respect to each other, right? But if they're actually truly independent, then it's actually safe to allow them to map in parallel, right? Even though they're going to map to the same instance, they're using disjoint subregions, right, on that instance, and therefore it's safe to allow them to map in parallel.
With the execution, and the execution doesn't matter, or will this new dependence be captured by Realm when you make the task?
So I mean, that's actually a good point. So actually, if you record a mapping dependence, right, in the trigger dependence analysis stage, the logical dependence analysis stage, it's possible for you to later figure out that there's actually no dependence when you actually issue them, do the physical analysis here in the trigger mapping stage. And we'll actually see some cases where we actually do imprecise analysis here. So actually, like, we have to be sound. If there needs to be a dependence, we have to express one here in the dependence analysis stage. But we can actually be like imprecise. We can actually record unnecessary dependencies in this stage if we're not sure. And then when we do a more precise physical analysis, we'll actually resolve that and realize that, oh wait, we could actually, there's actually no dependence here. And when we issue it to Realm, we'll actually, still enable us to find the parallelism, right? So like recording mapping dependencies here just guarantees that you get trigger mapping calls in order, right? But then you could eventually prove that something is actually parallel later. The thing you can't do is like unsafely miss a dependence here and then try to recover it here. That you can't do. So, but to your question, like, in the disjoint case that you gave, where like the two tasks are actually accessing independent subregions, right? You actually don't need to record a dependence here, even if they're going to map to the same instance. As long as their logical regions are non-interfering with each other, you don't have to record a dependence here. The physical analysis here will be able to run in parallel.
And correspondingly, the tasks may run in either order, even though they touch the same buffer. But
that's right. Yeah.
Owing to the fact that they touch different halves of it.
That's right. They might map in either order, and they might execute in either order, right? Like effectively you don't need any dependence analysis or any dependencies between them after that point. Effectively, if you can prove something is non-interfering in this stage, it's always very good just to let them go in parallel for this pipeline, right? So.
So I have a question about the mapping dependencies. So what is the API to specify the mapping dependencies?
Well, that's a topic of a future session. I'm telling you that they do exist and you can add them. We will look at how we add those in a future session, I promise. We will actually go through an example of how we traverse the region trees and look for dependencies between logical regions and stuff from different tasks.
Okay, so
and then how we add them.
Is it the user level API, or is it taken care of by?
No. This is all inside of Legion. Like everything we're doing here is inside of Legion and invisible to the user, right? Like the user just has to say like launch tasks in program order and name the regions they use, right? And the privileges and fields and other stuff. And then Legion is gonna figure out where all the dependencies are for them.
Okay, got it. Thanks.
Yep. Yeah, I'll be happy to show you guys exactly how we add logical dependencies between operations and tasks and other things in a future session. Okay, if you guys think of future questions, you can either email them to me. What I will probably do is probably not respond right away. I will probably just like do them at the beginning of the next session on Legion, and that way, like, we'll record the answers and everybody else can hear the answers as well, so that they're saved for posterity. Next week we'll be doing a Realm session to get started on Realm, so that the folks who need to learn about Realm can actually start learning what they need to know as well. So like if you're just looking for the Legion sessions, you can skip next week and show up 2 weeks from now. Otherwise, I guess I will talk to you guys all next week. Thanks for coming to the kickoff.